Welcome back to this Forge College Explainer. Seriously, I am thrilled to have you guys here. In our last lesson, Execution Model Overview, EVM and SVM, we laid down some heavy foundational concepts about state transitions and determinism. We figured out that getting an entire decentralized network to agree on a final state relies entirely on how we execute the code. Well, today we're getting incredibly concrete. We are going to trace exactly how that execution happens under the hood.
You know that feeling when you click send on a crypto transaction, watch that little loading spinner, and just kind of feel like your data vanished into some mysterious digital ether? Well, I promise you, it didn't. There is a highly structured and honestly sometimes totally chaotic process happening behind the scenes. Today, you and I are putting on our high-vis vests. We are becoming transaction traffic controllers to see exactly where those transactions go. Okay, let's dive right in. Here's our architectural blueprint for today's explainer. We're going to hit 1, the transaction lifecycle pipeline, 2, EVM, the assembly line, 3, SVM, the multi-lane highway, 4, Alice, Bob, and account conflicts, and finally, 5, designing for parallel performance. Let's get to it.
Starting things off with Section 1, the transaction lifecycle pipeline.
Before we can really compare different blockchain architectures, we've got to map out the actual chronological journey that every single transaction has to take, from the exact moment you click send to the moment it's permanently etched into the ledger. Think of this journey as a pipeline with 5 main checkpoints. First is submission, where the client signs the data. Next up is staging out in the network. Then comes ordering, execution, and finally, finality. Now listen, here's an absolutely crucial distinction right off the bat. At step 1, your cryptographic signature proves authentication. It proves you intended to make the trade, but it does not determine execution order. Ordering, that emerges much later in the pipeline.
Which brings us perfectly to Section 2, EVM, the assembly line. So how exactly does the Ethereum virtual machine handle this staging step? Well, in the EVM, the staging layer is called the mempool. And I like to describe the EVM mempool as, well, a totally chaotic, bribe-fueled battleground. Honestly, it's essentially a massive mosh pit. All the pending transactions are thrown in there together, just shouting, hey, take my fee and process me first. The nodes basically look into this mosh pit and cherry-pick the transactions that offer the best financial incentive. Once your transaction is lucky enough to get pulled from that mosh pit, it hits the EVM assembly line. The mechanics here are highly deterministic, sure, but they are incredibly rigid. I want you to imagine a single conveyor belt. Every transaction is a package, and they must, no exceptions, be processed one at a time. To keep the whole thing from breaking, the EVM uses nonces, which are basically sequential ticket numbers for your account, to enforce a strict order. But here's the joke, right? It's like getting stuck behind someone paying in pennies at the grocery store. If you're on a single conveyor belt and the package right in front of you gets stuck because it didn't pay a high enough fee, you are stuck too. Downstream packages literally just have to sit there and wait. All right, let's shift gears. Section 3, SVM, the multi-lane highway. Let's see how Solana approaches this. Now, to really grasp how the SVM builds a totally different model, we absolutely must lock down this one concept first, the account footprint. This is simply the specific list of accounts or resources that a transaction is going to touch, read, or alter during execution. Why is this such a big deal? Because knowing that footprint in advance is the golden ticket. It's the key that allows the SVM to process multiple, completely different things at the exact same time. So toss out that single conveyor belt idea. The SVM uses what we'll call highway mechanics. First off, there is no traditional global mempool. Transactions are sent straight to a leader for sequencing. I want you to imagine this leader as a highly stressed but unbelievably efficient traffic controller. Because the leader actually knows every single transaction's account footprint up front, it can say, okay, these cars are going to completely different destinations. I'll just put them in parallel lanes. Boom, concurrent execution.
Let's put these two head-to-head, assembly line versus multi-lane highway. The fundamental difference here boils down to how they handle conflicts. The EVM pushes conflict management into the ordering phase using those strict sequential nonces. You just wait your turn in a single file line. The SVM, on the other hand, pushes conflict management into parallel scheduling. It dynamically figures out who can drive next to whom without causing a massive pileup. Now, the really fascinating part is how we map these philosophies to our 5-step pipeline. Look at staging. EVM relies on fee pressure and a global mempool. SVM uses leader-centric scheduling. Ordering, EVM uses nonces. SVM uses leader slots. Execution is where it gets crazy. EVM is strictly sequential and single-threaded, whereas SVM is concurrent, again, as long as the accounts don't conflict. And check out that conflict detection row. The EVM finds out about conflicts during execution. The SVM? It calculates it beforehand, during scheduling. Ultimately, they both reach finality through consensus, but man, the routes they take to get there couldn't be more different.
Let's make this concrete. Section 4, Alice, Bob, and account conflicts. Let's bring this high-level theory down to earth with a classic token transfer scenario involving Alice, Bob, and Carol. First up, the EVM scenario. Let's say Alice fires off 2 transactions at the exact same time. Transaction 1 is to Bob using nonce-n. Transaction 2 is to Carol using nonce-n+1. Because the EVM strictly enforces sequential nonces, the miner absolutely must process transaction 1 first. Transaction 2 is entirely at the mercy of transaction 1's progress. If transaction 1 has a low fee and gets stuck in the mosh pit, transaction 2 is blocked from executing. Period. No way around it.
Now flip over to the SVM scenario. Alice sends those exact same 2 transactions. The leader receives them and instantly detects an overlapping footprint. Both of these transactions are trying to deduct funds from Alice's single account. Because of this overlap, the scheduler steps in and forces them to execute sequentially. Look, the SVM isn't magic, right? You literally can't drive 2 cars in the same parallel lane if they are trying to touch the exact same account. The state has to be protected.
And honestly, this brilliantly illustrates a massive implication for network security and MEV, or maximal extractable value. Because the EVM mempool globally exposes every pending transaction before execution, it basically creates this huge window for attackers to front-run your trades. SVM's leader-driven sequencing, however, rapidly accepts and schedules transactions. That significantly shrinks the visibility window, fundamentally altering how front-running even works on the network. A real game changer.
Which brings us to the practical part. Section 5, Designing for Parallel Performance. So what is the so what for you as a developer? If you're building Web3 apps, your architectural choices literally dictate whether your app flies or gets bogged down. Here is your actionable developer workflow. Step 1, enumerate every single account your transaction is going to touch. Step 2, check for overlapping footprints across simultaneous users. Step 3, make a tough structural decision. Do you enforce order or can you partition your app state across multiple accounts? And step 4, batch your submissions to maximize that SVM concurrency. You want to write your code so that the traffic controller can confidently assign your users to as many open lanes as humanly possible. If you take nothing else away from this explainer, let it be this golden rule. Disjoint account footprints enable concurrency. Shared footprints force serialization. Let me say that again. Disjoint footprints equal concurrency. Shared footprints equal serialization. If your application forces 1,000 users to touch one single master account, congratulations. You've just built a clunky assembly line right in the middle of a multi-lane highway. As we wrap up today's explainer, it's time to look ahead. We've traced the whole journey from submission all the way to finality. For our next lesson in this module, contract execution and parallelism, I want you to do a little homework. Try mapping out your own smart contracts account footprints. Find where your overlaps are. So, I'll leave you with this provocative thought. When you deploy your next application, is the architecture you've chosen going to create a massive gridlock traffic jam, or is it going to be a wide open, high-speed highway? Think about it. Thank you so much for joining me for this Forge College Explainer. To master these architectural deep dives and take your Web3 development skills to the absolute next level, make sure you visit forge.college. Keep building, stay curious, and I'll see you in the next one.